Welcome to the next talk in the Baikonur bunker. This is David Madliner, and he'll tell you stuff about inertial navigation, which means know where you are when you're blind, and death. So, yes, David Madliner, give him a warm round of applause.
So, thank you. Some of you might think, oh, a déjà vu, he's on top again. Well, this talk was a talk of a colleague of mine, but he couldn't come, so I will jump in. Sadly, I won't be talking about filtering, but this will be a very basic talk to understand the basics of inertial navigation. So, and rigid bodies. Okay, so let's get started. So I will have a short introduction about the nature of inertial navigation, and then we'll talk a little bit about mechanics. And finally, I will, it's not mentioned here, I will talk about a special sensor that we will use in some of our experiments in the future to navigate. So there are always some fundamental questions when you go through the world. Like, where am I? Where am I going to? How far is it away, and how long will it take? Okay, these are very simple questions. Every one of us solves them in his or her way when walking through a city, planning the next voyage, something like that. It's so fundamental that, well, it's a basic of every living being to know where it is and to navigate his surroundings. And of course, there are some fundamentals of space and time that we all take implicitly for being true, but just like, let us elaborate on them. So, you can measure distances and angles by coincidence of bodies. That is, you take something, put it against something else, and you say, okay, it's the same length, so you make a coincidence. And if you're measuring an angle, then you make a coincidence between a scala and some points on the scala. What you do if you measure a distance or an angle, you normally measure coincidences of bodies. So, for example, if you go through a landscape, then you see, oh, I'm at this point. I remember this tree. So you are standing right beside the tree, and this is coincidence of bodies, of your body and the tree. So, then, some thousand years ago, Hipparchus was one of the first to write it down. People noticed that the angles between stars are constant. So even if the stars move at the firmament, the angular distance appears constant throughout the night, except for some strange stars that seem to be moving, and they are very bright, and they call them planets. So space has 3 dimensions. Okay, everybody knows that, but Descartes wrote it. And planets travel along canonical cuts. So these strange bright stars that move through the sky, they behave in a certain way that we can calculate, and there are conical cuts. That is, it could be a circle, an ellipse, a parabola or hyperbola. And it wasn't quite clear until Kepler, looking at the observations by his colleague Tycho Brahe, figured it out in, I think it was 1604-5 or so, but he published it very much later, 10 years later or so. So, then again, from Kepler's law, Newton found that all bodies attract each other by gravity. Be it that the Earth attracts us or an apple, or the Sun attracts the Earth, or the Earth attracts the Moon, and vice versa. There's always some connection by gravity. And then again, Newton said, there's a time, and it's the absolute mathematical time. It exists, and it just flows. Okay, so. And we had clocks, and clocks measure time, until there came Mach. And Mach said, no, clocks just measure relative motion. That's point 1. So we had a problem as physicists, not as human beings, but as physicists, somehow time has disappeared. So this problem is not solved till this date, but we've made it more complicated. First, we saw that the speed of light in vacuum is constant. This is the so-called Michelson-Morley interferometer experiment performed in the 1890s. for a very complicated instrument with very large masses involved. And what they found was nothing. So when they found nothing, they knew that something was wrong, either with the experiment or with light. And Einstein took this and said, well, yeah, if this is true, if the speed of light and vacuum is constant, then space and time are not independent. Wow. So we have not two different entities anymore. And to be more precise, space and time, space-time, is curved by gravity. Holy Moses. So since then, we have learned not so much new, but this is our fundamental information we have about space and time. When we move through space, we always think in 3 dimensions. We always think about how to take the next step. There will be something because gravity is always pulling me down on Earth. I will not float away into space or something like that. So this is a model we have in our conscience, how the world works. Yeah? So there are some corollaries from these fundamentals, that distances and angles can be measured with light. And today we do that a lot. So in construction, for example, or in with geometry, or just by measuring the distance from Earth to the Moon or to some planets, we use light, laser, or radar. And a coordinate system is established by measuring angles and distances. So that's what geometry is about, measurement of the Earth. Okay, and again, if you can establish a coordinate system and use some math, then you can understand how the planets move, and you can calculate the trajectories. And stars are actually moving, but they are so far away that normally we don't notice that they are moving. So for very, very far bright sources like quasars or so, we can assume that they're standing still in space and they are, at the moment, the best points in space to navigate. Of course, not when you're on a ship, okay? But on a broader angle. So, navigation. It's about finding the position. Position can be deduced from observation of reference, objects, and time. So, no navigation without a clock, but a clock is easily attainable and you can be moved with you, and today it's absolutely no problem and everybody uses it without knowing that it has a clock with him. But reference objects, it's much more difficult. The problem is, sometimes there are no reference objects because you cannot see anything. Maybe it's foggy, maybe it's dark, maybe you're in space. Or maybe someone is trying to put something in the way so you're not seeing where you're going. For example, in a war, when you have a rocket, then a missile, for example, then the enemy will try everything to counteract the electronics of the rocket. So it cannot, for example, look for, it's called in German, Funkfeuer. So for telemetry, auto-telemetry, it will be obscured. So there is a method that does not rely on any outer observation. It's called dead reckoning. And dead reckoning was invented in the time when the first sailors went to the ocean, far out away, where there were no other reference objects than stars. And it's based on the measurement of quantities of motion. So what the sailors did was putting a cord into the water, and there were nodes on it, and then, or knots, and they measured the velocity in knots. And from this velocity and the angle they were following, they calculated the distance they were traveling, and so the position on the ocean. It was, of course, very error-prone, and they always tried to refine it by observing the stars and calculating with a clock the latitude and longitude. So, but if you use dead reckoning, you don't have to look at the stars. So what are these quantities of motion we can use? There's a displacement r. For example, if you're in the dark, you just try to keep your hands to the wall. So you measure the distance to the wall, and you know if I have touch with the wall, I can go around, and I won't be too far from the wall. You can measure some angle phi. So, for example, if you're in a desert, and you don't know where to look, and you just can try to construct you an angle and go in this direction, yeah, by just looking at something that is visible. You can measure the velocity. with very different means. For example, in an airplane, you can use a pitot tube to measure the relative velocity with the air, so you don't have to rely on external measurements, just a measurement of the velocity of air right beyond you. Or like the sailors did, the velocity above water. You could measure the angular velocity, so you can recalculate your attitude. There was some device in old China, I don't know what was it called, the south pointing, I don't know, it was a chariot, and there was an arrow positioned on it, and they had some nice gears, and when the thing turned, the arrow always pointed in this direction. So they integrated the angular velocity in a sense. And you can calculate your position from measuring the acceleration. So measuring acceleration is not very difficult if one understands how Newton's law works. What you have to do is take a mass, a probe mass, hang it in space with something, something that holds it back elastically, and then measure how it moves, how it is accelerated. And by measuring that, you measure your own movement, your own acceleration, and you can, by double integration, get to your position. Of course, there's a problem that you may be changing your attitude. We'll talk about that later. So, and then you can measure angular acceleration and even higher derivatives. So these are the quantities of motion one is interested to attain during that reckoning. So these are indirect, deduced observables that are not directly connected to your absolute position in space. So as one example, the so-called differential drive, some of you may have experimented with that. It's just what you have if you have a two-wheeled robot, and you can control every wheel with, like, say, a stepper motor or a servo with incremental encoders. So what you get is, essentially, if you're on a flat plane, then you have three parameters to describe the position and attitude of your robot. It is the angle phi and the Cartesian coordinates x and y. So, and if you start at some certain point in space and you observe just the angular velocity of your wheels, and of course you have to assume there's no slipping. That's a problem. It depends on the ground. If there is no slipping, then you have the connection to the three parameters to describe the absolute position in the reference plane. So on the left you have the first equation for the angle phi, the second is for x, and the third is for y. So, without going into much details, this is an ordinary differential equation, and you can solve it with different ways. So it's an initial value problem. In a sense, x is the phase vector, saying having every information, and the evolution of this phase of your position in time in this case, but this can be much more complicated, is dependent on only one variable of time. So you know that you are moving through space and time. And even if you have a higher order of differential equation, like for example, if you are measuring the acceleration, which is the second derivative of your position in time, then you can reduce this differential equation to first order every time. It's no problem. So in the end, you're always left with this problem. So the phase vector contains all information, like for example, in the case of the robot, the coordinates x, y, and the angle phi, and in the case of a body like ourselves, it would be 6 degrees of freedom. So this propagator function f that I've written describes how the motion through space phase is done and is normally the forces that act on the body. So you start at some point, anywhere. You have to find the point. Maybe if you're looking at a plane or a rocket or just a wheeled something, then you choose the GPS coordinates, okay? This is your starting point. And from then you can integrate then where you're going. So how do you integrate an ordinary differential equation? There are four often used methods. The first is Euler, the second Verlet, Runge-Kutta, Fehlberg, and Bulle-Stör are the most employed. There are others, but these are all fairly simple. I will only explain one. I will explain Runge-Kutta, which is very sophisticated and easy to implement. So essentially, you have to write down the propagator. This is the propagator, okay? And it depends on the problem. I won't do that explicitly. It depends on what you are trying to simulate. And then you have a sequence of phase points. It's like, I'm now here, the next moment I'm there, and so on. So you always have some discrete stepping time. I call it delta t. So this one over there, this is the delta t. There. So this delta t has to be discrete because our computers are discrete. You cannot continually compute something. If the time is too short, he would never enter compute. So what you essentially do, you take the point where you're standing, x or n, and then you add 4 correction terms. This is the first line. These 4 correction terms are calculated by the formula you see here. You don't have to understand this completely. You just have to type it in your program, and it gets out correctly. And the best thing to prove that you're doing it right is trying to solve an ordinary differential equation where you know the solution, and you can compare your solution to your ordinary differential equation's exact solution, and then you know, okay, my integrator is right, and then you can just use it. So, and what do we use it for? Well, in the case of inertial navigation, you use it for the movement of a rigid body. A rigid body is just an arbitrary distribution of mass that does not elastically deform. So this is a very simple model. Of course, everything in this world is elastic. There's nothing like a rigid body in this universe. But as a mathematical approximation, it is quite good to get navigation going. So the most important theorem in all what is interesting us here is just Euler's theorem of the motion of a rigid body. You just need 6 free parameters. This is a translation in 3 dimensions and a rotation with 3 parameters. So what you essentially have is you have an inertial system with some origin O, maybe the point where the rigid body started, and you have some directions you defined. I call him here E, I, star. So this is a fixed set of base vectors in space. Okay, of course you don't have to draw them down. You have just to know E1 is, for example, in the direction of east, and E2 is in the direction of north or something like that, and E3 would be up, okay, for example. So and then you know that every movement of the body can be described by giving some vector, R, the vector of the position of the center of gravity, for example, of the body, and then you have to describe the attitude of the body, so how it turned. And this is a second set of base vectors that I just call EY. So the most difficult thing is to get from the inertial base vector system to the tilted one. So it changes attitude, it doesn't deform, and this leaves only one mathematical operation, so-called rotations. And rotations or base transformations are just linear maps that transform a vector into another one, but thereby obeying certain rules. And these rules are very simple, and the mathematics say, okay, it's in the special orthogonal group with 3 dimensions, and the corresponding matrix is sometimes called the directional cosine matrix because it contains all the cosines of all pairs of base vectors. So you have 9 cosines, 3 times 3. So importantly, the determinant of this matrix has to be 1. So there is no mirroring. So when you move through space, none of the x's will invert and somehow a right hand will convert into a left hand. It doesn't happen ever. So this is why it has to be +1. And very important, to get the inverse of such a directional cosine matrix, you have just to transpose it. It's very easy. So this matrix transforms So the matrix that corresponds to this linear map transforms from the coordinates in the body back into the inertial frame. So if you have some vector in your body system, you just multiply it with this matrix and you get the vector in the inertial system. Okay, so much. I won't make it more complicated than that. So this is the so-called strap-down algorithm, where you have your rigid body, like for example a rocket, and you put on a sensor that can measure acceleration and angular velocities. And it is strapped down. So there are other possibilities. You may have a sensor platform that is gimbaled, that is in a cardantic joint, so it doesn't move in space. So when you turn the body, the platform just stays right where it is. But this is mechanically very complicated. And it is much easier to just strap down, to fixate the sensors on the rigid body, so the sensors have to move together with the frame of the body. So then the sensor will, of course, measure the acceleration in the body frame. When it's moving with the body frame, then it has to measure exactly what is happening in the body. And that is not what you want to have. You want to have the acceleration in inertial systems, so you can just double integrate it with the Runge-Kutta and then get your position in space. So what you have to do is to take this acceleration A that you just measured and multiply it with your rotation matrix, and then you get the components of the acceleration in the inertial system. And then you can, from this, in part 3, you can then calculate the new position in space from the acceleration, just by double integrating it. So you have a velocity in mind, and you add something to the velocity to the acceleration, and something to space to the velocity. And then in step 4, you have to update the rotation matrix with the angular velocities you measure, because the angular velocities is indeed exactly the change of your body base. So the three, let's go back for, oh, sorry, just to show you. So these three vectors are changing in time due to the angular velocity that you are measuring in the body system, okay? So you have to transform them back into inertial system and then adjust the rotation matrix. If anyone is interested, we have a code running, so you can just have a look at it, how it works. So, okay. And after you have updated it, you have to repeat it, because this is a continuous process, and the faster you do it, the better the resolution will be. So after this point, normally one would say, okay, now I know where I am, I can go around and it's no problem. But there is a problem. The problem is in the measurement of the angular velocity and the acceleration, because every measurement in the physical world is prone to errors. There's always an error. And to make matters worse, this error can depend on the state of the motion. So if one is going very fast and accelerating very fast, maybe the errors the sensors are producing may get higher. This is a normal, it's a mechanical system, and if you have something with springs or so inside and you push it with a hammer, it will start to resonate and make such strange things. And an accelerometer is essentially a mass hold with springs. And if you have very great jerks and accelerations, then they may have got out, well, errors, more errors than before. So, and of course, these systems that measures the acceleration is not at 0 Kelvin. So you always have thermal errors. You always have the problem to deal with that what you are getting out of your sensor is not the true acceleration, but something in the vicinity. So to get rid of this, you need to filter. I won't be talking today about filtering because the guy that does the filter isn't here. But to give you an idea, for example, a particle filter, what you do is you have not only one XN, not only one model of your path you're going, but you take an ensemble, lots of them, let's say 1,000 or so. And then you give every one of them a certain probability of the system being there. And the algorithm then propagates, using this, essentially, propagates this ensemble of particles through phase space. And every time you get new information, like for example, for additional sensors like GPS or so, you can look at your particle filters and just throw away all the particles that are improbable, too improbable. So you get like a cloud of particles moving through phase space, and you can say, okay, I am somewhere in there, and you can give an error interval. Yes? Okay, instead of continuing this, I will show you a sensor we will use. So, I'm not from Analog Devices. They just make the best sensors. I cannot deal with it. It's the way it is. So this is the data sheet of the ARDIS 16400 or 405. And it has some very nice features. So this is a system that essentially measures the acceleration in 3 dimensions, the angular velocities in 3 dimensions, and the magnetic field. So one has an additional information if the magnetic field is to be trusted. This is a problem, for example, rockets. A rocket motor produces very high temperature plasma. So as you know, when plasma moves, there is a current. And so a rocket motor essentially produces a lot of magnetic fields, electric fields, when it's working. So one has to be careful during rocket run if the magnetometer is to be trusted. So it measures these things, and you can just power it up. It's a small box. Let's see if we can see the box, just so you have a feel how it looks like. So this is the box. It's about 23 millimeters by 23 by 23. So it's just a little cube. And this little cube gives you everything over the SPI. So you just plug it in, give it 5 volts or so, and it will start streaming the data. You just get it and put it into your algorithm. This only problem with this device is that it costs a lot of money. So this one is about $500 to $700 if you buy 1,000 pieces. Okay? This is high-end equipment. This is not, of course you can buy more cheaper accelerometers. Today there are accelerometers with €5 or so per piece. It's possible. The problem is only that they have a much larger error bound. Let's see what this little thingy can do. So, very important is always to look at the parameters of operation. So, just put this away. There are certain things that you have to think about. For example, will your object move faster than 300 degrees per second? So faster than about 1 turn per second. Because this little thing can only measure up to 350 degrees per second max. So if it's rotating faster, you have to use another sensor or additionally another sensor. So you have to be within this dynamic range. And then of course you have to think about the interval of temperature. Well, for this little thing it's okay, it's from -40 to 85. And it's calibrated, so it won't change too much. Of course, in a rocket, the temperature can fall below -40 degrees if you're up, so you have to think about some temperature stabilizing. And then they talk here, for example, a very important parameter is the bias error. So if you just put it on a table without moving, it will give you a 1 sigma of 3 degrees per second. Yeah? Would be away. So you have to recalibrate it. And for example, angular random walk. So you have here 2 degrees per root hour. So if you just put it on a table and let it integrate, then it will just move around by 1-2 degrees per hour. It's not changeable. And other sensors are much worse, much worse. So this is a very good sensor. And you have here, for example, a bandwidth of about 330 hertz. So you cannot go much beyond that update rate. So you should, for example, ask every 100 seconds for the parameters and let your integrator run, okay? So acceleration for rockets is very important. For normal applications, it's not so crucial, but for example, it can go to plus minus 18 G, and our rockets go to plus 25 G. So at the moment it crosses this 18 G, the output of the accelerometer is just not usable. It just hits the roof and you have to use some other sensor. Well, let's see, what's one of the, this magnetometer was one very, misalignment. Yes, this is very interesting. Here for the accelerometers, misalignment, 0.2 degrees. So the accelerometer's axis are misaligned by 0.2 degrees from axis to axis. So if you, for example, take an accelerometer chip that has only one axis and you put another one, the second axis, on a board, then you have to achieve 0.2 seconds degree to be better than that. It's complicated because the accelerometer inside of the package is misaligned too, so you don't know where it is aligned. So actually what you have to do is you just build your board, hope for the best, and then measure the misalignment by making tests and then put it into the error algorithm, the filtering algorithm. So what else is very important? Oh, so much. Okay, I think that's for today. So thank you for your attention. Any questions?
Yeah, you.
Hi, so I was wondering about these sensors. Do they all follow one physical principle, or are there sensors that follow like different physical principles? So
Yes, there are. Well, the MEMS sensors you now can buy for so cheap money. These micro machine sensors, they follow almost all the same principle as I know. So the sensors for the angular velocity, they use a tuning fork that has a certain vibration frequency, and due to Coriolis forces during rotation, this resonant frequency changes, and you can pick up this with a condensator. So this is the main principle to measure the angular velocity with these small devices. But there are, of course, physical principles that are much more precise. For example, using a Sagnac interferometer, that is laser light going in two different directions and then making interferometry. And this is much more precise, so-called gyro lasers, but they are very costly units, so you can spend 10,000 euro for only one axis. Okay?
So when you're taking different sensors of different physical principles that have different error rates and different magnitudes of angle and velocity, have you then played with sensor fusion and common filters, and then what is like the standard confidence interval you get out of it? Like what is the best you could go for?
Well, I would like to answer this question. The problem is that the guy that is specialized in this region isn't here, but I can tell you so much. It's always better to have more information. So even if you have a bad sensor, as long as you know that it's bad, that is, you can give some error distribution, you can get more information out of it. Okay, but it's a much better idea to not just use accelerometers and angular velocity sensors, but also to use additional observables that have nothing to do with acceleration or angular velocity. For example, we are using a horizon sensor, which is essentially an assembly of at least 8 infrared detectors, 8 photodiodes that have a spectral window around 5 to 10 microns, so they are looking at the infrared, and they look just upwards and downwards. So we pattern on the circumference of the rocket, so you have always 2 pairs of sensors that look upwards and downwards. And the thing is that in this spectral range, you only see the Earth or space. You don't see clouds, you don't see water, nothing like that, so it's transparent. So what you essentially do with the sensor, you can measure the horizon. And you can measure the angular inclination of the rocket. And this is an additional information that will, of course, help you when you are filtering to get out the bad choices you made. Okay? And there are a lot of possible principles. For example, you could do telemetry, but this is not really inertial navigation. But you should use it in sensor fusion. If you have any information at all, put it into the mix. Okay?
So, next question.
So, in your previous talk, you were talking about having rockets with burn times of a second or so, so obviously very, very high accelerations. What kind of accelerometers are you using to be able to deal with that kind of acceleration?
Yes. At the moment, we had an ADXL250. I don't know if it's even built anymore. There surely are a new prototypes from different companies. So we use the ADXL250 that goes to 50 Gs plus minus. The only problem is that it has only 2 axes, so we had to put the third axis like on top of the board, and it was not very, very nice. But there are from Freescale, I don't remember the number, mm something 12, I don't know. And it's just plain in the plane of the board, and it has one accelerometer that goes upwards, and I think it goes to 50 G2. So there are in the market, there are very good accelerometers for up to 1000 G or so. But of course, this is a very short period of time, so after that, this normal accelerometer would pick up again.
Any more questions? Okay.
1 second, please. The filter you are talking about, is it a Kalman filter?
This is one filter. This is one filter you can use. The Kalman filter is very sophisticated in the sense that it's a filter that are easier to include the sensor fusion and reject some models. This has answers your question. Okay. So
more questions? Somewhere there? Okay.
So, is it an extended Kalman filter? And can you tell me how many states you have?
I don't know. I simply don't know. I only know it's written in assembler, it runs on a P8X32A, and it does well. I'm sorry, I cannot answer that.
So, are there any more questions? Then I would ask you for a warm round of applause for our speaker.
Thank you. Oh, right.